This problem is from the 2023 Harvard-MIT Math Tournament. Feel free to give it a shot and keep watching to see the solution. Okay, with these kinds of problems, there are usually multiple ways to solve them. So I'll show two ways. The first way is using engineer's induction to find a pattern. So basically engineer's induction is figuring out what the first couple terms look like A2, A3, A4, and then looking for a pattern and then seeing if you can prove that pattern. The other approach that I'll show involves converting this recurrence into a linear one. The second one's faster, but if you have another approach, another way of doing things, feel free to share it in the comments because I'd like to encourage discussion. Okay, but I'll include the timestamp to the second approach in the comments. Okay, so here's how to do it. So they're asking for A100, and since 100 is a large number, we want to find an explicit formula for AN. So how do we find AN? Well, if you're unsure of where to begin, with these kinds of problems, you can start by calculating the first few terms and looking for a pattern. So we've got A1, but using this recurrence, what would A2 be in terms of A1? So it would be, so K is 2, so change K to 2 there. A2 minus 1, A2 minus 1 minus 2 minus 1. Okay, and we can simplify this. Minus 1. Okay, nothing too special here. Let's try A3. Okay, so it's going to be, so this time K is 3. So 3 times A2 over A2 minus how much? Minus 2. Okay, and what's A2 again? A2 is 2A1 over A1 plus 1. And we can try to simplify this. So you'll notice that we've got fractions in the numerator and the denominator of this big fraction here. So, but the denominators of these fractions are the same. So how do we get rid of them? We can multiply the top and bottom by A1 minus 1. Okay, so what does this give us? This is going to give us, so we're just left with this over, so this minus 2 times this. So that's equal to, this goes away. This is just positive 1. Oh, this is not just positive. Okay, so actually this simplifies as, my bad. Okay, so this is going to be over 2. So this is 3A1. Okay. Yeah, so A3 is equal to 3A1. This is nice. This is very simple. Let's keep going. What would A4 be in terms of A1? So A4 is equal to 4 times A3 over A3 minus 3 is equal to 4 times A3 is 3A1 over 3A1 minus 3, 12A1 over 3A is 3 is equal to 4A1 over, so I just divide the top and bottom by 3 here. Cool. Nothing too special here though. How about A5? That's going to be equal to, let's look at the recurrence again. 5 times A4 over A4 minus 4. Okay, and then A4 is this, so I change A4 to this, and this one to this as well. Okay, so 5 times 4A1 over A1 minus 1. Careful here. Okay, so we're gonna do something, we're gonna do the exact same idea here. Okay, so then that would give you 20a1, right? This is gonna go away. And then this one gets multiplied by a1 minus 1. Okay, and this is gonna be over 4, right? Because this times this is positive 4. Okay, so then this simplifies to 5a1. Okay, so this is nice, this is nice. I wonder if this pattern continues for the odd numbers. And if there's a pattern like this for the even numbers as well. There could be. But, okay, let's see if there's a pattern with the evens. Okay. So, to check if there's a pattern with the evens, we're going to start with A2. And then see what we get for A3 in terms of A2. And then plug that in for A4. Okay, so A3 in terms of A2, let's use this again. What's K going to be? K is going to be 3 times A2 over A2 minus 2. Okay, then A4 is how much in terms of A2? So again, we're going to use this. K is 4 this time, so 4 times A3 over A3 minus 3. Okay, so then this is equal to 4 times, well, A3 is this, so let's change it to that. Okay. Okay, and then it's the same idea. To get rid of this and this, we'll multiply the top and bottom by A2 minus 2 over A2 minus 2. Okay, so 12A2 over 3A2 minus 3 times this. Okay. Let's divide the top and bottom by 3. Okay, so then this is equal to 2A2. Okay, so this is nice as well. Now I wonder what it would be for A6. So let's do A5 and A6. My theory here is A6 is going to be, let's see. Okay, I'm not sure yet. Let's just do A5. So that's going to be 5A4, right? Because K is 5 over A4 minus 4. Okay, so A4 is how much? A4 would be, oh, A4 is this. Okay, so 5 times 2A2 over 2A2 minus 4. Okay, so 10A2, 2A2 minus 4, divide the top and bottom by 2. Okay, nothing too special here. I didn't expect anything too special here. I only expect something special with the evens. Because earlier it was with the odds. Okay, so then, what would it be for A6? So plug in 6. Okay, so 6A5 over A5 minus 5. Okay, so that's going to be 6. So change A5 to this. Times 5A2 over A2 minus 2 over 5A2. Minus 5. Same idea here. Okay, so 30A2 over, this is gonna go away. Yeah, let's see. So it's gonna be 10 here. So 3A2. Okay. So I think I see a pattern here with the evens. It's equal to 1A2. So, you can prove this pattern with induction, I think. Yeah, we can prove it right now. Should we prove it for the odds or for the evens first? Let's do the odds first. Okay, so basically, we can make a claim. So claim, let's see here. For odd n, an is equal to, what did we have earlier? Okay, so this was our sheet earlier. It's gonna be n times a1. N times a1, and for even n, an is gonna be equal to what? N over 2 times a2. Okay, so we're gonna prove this by induction. Proof by induction. Why should we consider induction? Well, because we're proving something for all odd n, or for all even n, so that's when you want to consider induction. Okay, so it doesn't matter which one we start out with. Let's prove the first part, odd n. Okay, so base case. So when n is equal to 1, is it true? a1 is equal to 1 times a1. So that's true. Okay. Inductive step. Assume let's see. am is equal to m times a1. For all odd m less than or equal to. Okay, inductive step, assume that am is equal to m times a1 for all odd values, m less than or equal to n. Then what do we want to show? We want to show am plus 2 is equal to m plus 2 times a1. So basically show that this works for the next odd number. And how do we do that? Okay, so I think we can do that by plugging am into this, or using this recurrence to get am plus 1 and am plus 2. Okay, so let's see. From the recurrence, am plus 1 is equal to m plus 1 times am over am minus m, which is equal to, well, am is, we're going to use this. So m plus 1, oops, I forgot to put the parentheses there. M plus 1 times how much? am, okay, so m times a1 over m times a1 minus m. Okay, and then am plus 2 is equal to what? It is equal to, let's use the recurrence again. So m plus 2 times am plus 1 over am plus 1 minus m plus 1, which is equal to how much? M plus 2 times m plus 1 times m times a1 over m times a1 minus m over m plus 1 times m a1 over m a1 minus m minus m plus 1. And then we can multiply the top and bottom by this over itself. I'm going to get another sheet of paper real quick. Okay. So then am plus 2 is equal to m plus 2 times m plus 1 times m times a1 over m plus 1 times m times a1 times, minus this, so m plus 1 times this, m a1 minus m. This is equal to how much? Cross this out. We can also cross out m equals m plus 2 times a1 over a1 minus a1 minus 1. Oh wait, is it minus 1? Yeah, it is. Okay, so this is equal to m plus 2 times a1. And then, yeah, that proves it for the odds. Okay, for even n, what does this look like? Here, I'll just box this. Okay, for even n, it's a similar proof, but I'll do it for completeness. Okay, so n is equal to 2. All right, so again, this is what we're trying to prove here. Okay, let's see. So when n is equal to 2, so a2 is equal to 2 over 2 times a2. Okay, that's good. Okay, now the inductive step. Okay, so let's see, what did I say earlier? Yeah, I'll just copy and modify it for the evens. Assume am is equal to m over 2 times a2 for all even values, m less than or equal to n. We want to show am plus 2 is equal to m plus 2 over 2 times a2. From the recurrence, am plus 1 is how much? Am plus 1 is equal to okay, let's look at the recurrence again. Is equal to m plus 1, because we're plugging in m plus 1 for k here, times am over am minus m. Okay, what else? And then we want am plus 2. Am plus 2 is equal to m plus 2 times m plus 2 times am plus 1 over am plus 1 minus m plus 1. Okay. And then we would plug this in here. Okay, so it's equal to m plus 2 times m plus 1 times am over am minus m over oh yeah, okay, so we copy this again. M plus 1 times am over am minus m plus 1. I'm gonna get another sheet. Okay, and then we're gonna simplify this. Okay, so this is what? So that means am plus 2 is equal to, well, I multiply the top and bottom of this fraction by this over itself. So it's going to give me m plus 2 times m plus 1 times am over m plus, this is m plus 1 times am minus m plus 1 times this, am minus m. Okay. And then, let's see here. What does this simplify as? We can cross these out. Okay, so then this becomes m plus 2 times am over, well, this goes away, over m. But am was how much again? Oh, we could have been cleaner with this proof, because this would have worked for both odd, this would have worked for both odd and even. Oh well. Okay, we wrote it out already. We'll just keep it like this. Okay, am was m over 2 times a2. So m over 2 times a2. Okay, this goes away. Yeah, so then that's m plus 2 over 2a2. Cool. All right, now that we've proved these claims, we are ready to solve the problem. Okay, now that we've proven this claim, we're ready to solve the problem. And okay, so they told us a20 is equal to a23. Now, what's a20 in terms of a2? Well, first off, should we use the odd part or even part of this claim? The even part, because a20 is even. Okay, so a20 is equal to 20 over 2 times a2, which is equal to 10a2. And then for a23, should we use the odd part or even part of this claim? We should use the odd part because 23 is odd. Okay, since this is equal to this, that means 10a2 is equal to 23a1. Okay, and what else do we know about a1 and a2? Because if we can get another equation with just a1 and a2, we can solve the system of equations, and the problem will fall apart because we have this claim proven. Yeah, basically if we can find a2 from that system of equations, then we can find a100. Okay, so we can actually get another equation with a1 and a2 from this recurrence here. When we plug in k is equal to 2. So let's go ahead and do that. a2 is equal to 2 times a1 over a1 minus 1. Okay. So I think we should try to get a2 because from our let's see here. Yeah, because a2 would help us find a100. Okay, so How do we get A2? Okay, so I'm going to get A1 by itself and substitute it into this equation. That way we get an equation with only A2 in it. Okay, so 10 over 23 A2 is equal to A1. So that means this equation is going to turn into A2 is equal to 2 times 10 over 23 A2 over 10 over 23 A2 minus 1. Okay, let's multiply the top and bottom by 23. Okay, so this is 20A2 over 10A2 minus 23. It's A2. Okay, so 10A2 squared minus 23A2 is equal to 20A2. Let's be careful here though. 10A2 squared minus 43A2 is equal to 0. A2 times 10A2 minus 43 equals 0. A2 is equal to 43 over 10. So A100 is how much? If A2 is 43 over 10. I'll get another sheet of paper. Okay. If A2, since A2 is equal to 43 over 10, then A100 is how much? Well, it's going to be 100 over 2 times A2, so it equals 50 times A2, which is 43 over 10. 5 times 43, so 200, 215. This is your answer. Okay, here's a faster way to solve it by converting this recurrence into a linear one. Okay, so we want to convert this into a recurrence that's easier, one that we're familiar with solving. So, okay, so why are we converting to a linear recurrence? Well, you'll see AK on this side, and you'll see only AK minus 1 on the right-hand side. There's no AK minus 2, AK minus 3. So that's why I think it might be possible to convert it into a linear recurrence, but it would be much easier if this fraction was flipped, if we took the reciprocal. So, because then we could split it up. Like, okay, so for example, if we let BK be equal to 1 over AK, then, well, how do we get an equation with 1 over AK? By taking the reciprocal of both sides of this equation. So 1 over AK would be equal to AK minus 1 minus K minus 1 over K times AK minus 1. Okay, so now I can split this up and I can change this to BK. BK is equal to AK minus 1 over K times AK minus 1 minus K minus 1 over K times AK minus 1, which is equal to, this cancels, 1 over K minus 1 over K times, what's 1 over AK minus 1? That would be BK minus 1. So yeah, now we have a linear recurrence. Actually, this would have been simpler if we didn't even have to deal with the K's. So actually, we could do this. We could let BK be equal to K over AK. Yeah, so then if I were to multiply both sides of this equation by K, what do we get? So K over AK is equal to AK minus 1 minus K minus 1 over AK minus 1, which is equal to, so I split this up, so this divided by this is 1 minus K minus 1 over AK minus 1. And this is equal to BK minus 1. Okay, so yeah, this is BK. BK is equal to 1 minus BK minus 1. So BK minus, So what does this tell us about BK minus 2 and BK? from this, you'll notice that bk is equal to 1 minus. This is the same thing as 1 minus bk minus 2 if we shift the indices. So that means bk is equal to bk minus 2. Well, what would the motivation for this be? Probably similar to the first approach, just testing out small values, or maybe you'd arrive at maybe you'd arrive at that this way. I'm gonna get another sheet of paper. Okay, so yeah, that means bk is equal to bk minus 2, which is also equal to, if we shift the indices again, it's going to be bk minus 4 and so on. So bk equals bk minus 2 equals bk minus 4 equals dot dot dot. Yeah. So we've got, so now we want to find A100. If we can find B100, we can also find A100. Let's see here. From this equation, we have B100 is equal to 1 minus B99. And if we can get another equation with B99, B100, then we can solve the system of equations to get B100. Well, since B100 is equal to, from this equation, we've got B100 is equal to B98 equals B96 equals dot 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 equals B20. And B99 is equal to B97 equals B95 equals dot 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 equals B23. And we also know that let's see here. Well, we know that A20 is equal to A23 from the problem. So what does this say about B20 and B23? So BK is equal to K over AK. So AK is equal to K over BK. So A20 is 20 over B20. This is equal to 23 over B23. Okay, so then B20 is also the same as B100, and B23 is B99. Okay, so then now we have a system of two equations, and we can solve for B100. Let's see here. Okay, I'm gonna solve this system real quick with another sheet. Okay, so we've got B100 is equal to 1 minus B99, and 20 over B100 is equal to 23 over B99. Okay, so let's get B99 by itself here in this equation and plug it into here. So B99 is equal to 1 minus B100. Okay, so 20 over B100 is equal to 23 over 1 minus B100. Okay, so 20 minus 20 B100 is equal to 23 B100. 20 is equal to 43 B100. So 20 over 43 is equal to B100. So what is A100 equal to? So look at the recurrence again. So B100, so B100 is equal to 100 over A100. Okay, so 20 over 43 is equal to 100 over A100. Okay, so then Multiply both sides of the equation by a100, and then multiply by the reciprocal of this, times 43 over 20. I'm going to cross these out. And then 5 times 43 is 215. This is your answer.